In this lecture, we're going to continue looking at sequence alignment algorithms. So we're going to briefly take a look at local alignment, the Smith-Waterman algorithm, and then we're going to look at a slightly more complex algorithm, Hirschberg's algorithm, that is necessary to take up less space, so less memory requirements when aligning sequences. And we're going to see also substitution matrices. These are those matrices that tell us how to score each match or each substitution when in the alignment we are matching one nucleotide or one amino acid residue to a different one. So let's see the local alignment algorithm. The idea of the global alignment that we saw previously, the Needleman-Wunsch algorithm, for example, was to score and find the best alignment between two sequences, considering the whole sequences. We saw some variants of semi-global alignment where we could ignore penalties with gaps, so gap penalties at the extremities of the sequences, but we are still finding the global alignment, so aligning the complete sequences. The Smith-Waterman algorithm has a different purpose. This local alignment algorithm is not meant to give us an alignment for the complete sequences, but rather to identify subsequences that that have the greatest match. So basically we are going to look at subsequences of the two sequences we are considering that have the highest score when we align them. And the modification here to compute a local alignment is to, in addition to consider these branches that we saw previously for the computing the maximum score at each position in our alignment score matrix, we are going to consider also the possibility of matching the current residues. So we take the best alignment up to position I and position J in the two sequences, and then the score of matching these two residues, I from sequence A and J from sequence B. Or we can skip leaving a gap in one of the sequences and pay the gap penalty. So, for example, we consider the alignment of using everything up to position I of sequence A, but not using position J of sequence B. So we leave B paired with a gap, or we leave A paired with a gap. So in those cases, we pay the gap penalty here, which is a negative number. But for the local alignment, we're also going to consider a zero here. In other words, whenever the best result is negative, we just give it a zero and start over. So we ignore things that give an overall result of a negative score. So this means that when we initialize the matrix, instead of starting with the gap penalties going negative here on the first row and on the first column, we start at zero. So we ignore these kinds of alignments where we only have penalties, because those will not give us the optimal local alignment. And then during the process of filling this matrix, we use these four branches here. So whenever we find, for example, a case like on this cell here, if we find that either adding a gap on one sequence and then a gap on the other, which would give us -4, one of these branches, or doing the same thing on the other, from the other side, so the other branch will also give us a -4, or if we go on the diagonal and match T with C, we get a -1 because we have 0 from the previous alignment, which does not exist yet, but then we have to match this C with T, and if we assume, as we've been assuming, that when the symbols are different we have a penalty of 1, then this would give us a -1. But since all the possibilities are negative, we use the 0, which is the maximum here, and we set this at 0. So this is what we do to fill the whole matrix. And then instead of starting from the end, we're going to start from the best score here. So in this case, it could be from this cell or it could be from this one. This would give us two identically scoring alignments. And what we're going to do when we backtrace is to consider only this stretch of positive scores until we reach the first zero. So in this case, when we compute the alignment, note that we are not considering the C on the beginning of the top sequence, nor this T on the beginning of this bottom sequence here. So we are only aligning this part of this sequence, and we are only aligning up to here, onto this GA here at the end. So we are ignoring these extremities here. And this gives us just the alignment of the subsequences from both sequences that match the best. So that gives us the highest score. We could also start from here, since this is the same score, 3, and in this case we would only have this first alignment here. So TAA and TAA would be another possible solution for the local alignment with the same score. So basically the difference here is that we do not consider negative values on the matrix, so the minimum is 0, and then we start from the maximum score and trace back until we find a 0. Everything else that falls outside, so all of these residues here, we just ignore, and we only align the subsequences that have the highest match. So this is the local alignment algorithm. Okay, so both of these, the Smith-Waterman and the Needleman-Wunsch, and even with the variants that we saw for semi-global alignment, they all use the same approach of creating this matrix. However, this gives us a problem with large sequences, and that's why we have this Hirschberg's algorithm that can be used for large sequences. So when we compute these matrices for the alignment scores, we have a matrix that has as many rows as the length of the first sequence and as many columns as the length of the second sequence. So this means that we're going to do on the order of this number of computations to fill up the matrix, and this is the order of time that we're going to take. So basically, if we double the size of one sequence, we double the time we take to compute. If we double the size of both sequences, then we take 4 times longer to compute, and so on. This may be a problem if we're trying to do this with a large number of sequences, for example, to search a database, and we're going to see that problem later on a future lecture, but it's generally not a problem for aligning 2 sequences. Even if it takes a bit longer, it's okay, we just want to align those 2 sequences. The big problem is that building this matrix also requires this amount of memory space. So we need m by n cells on the matrix. Each cell may take several bytes of memory, but in any case, if we have 2 sequences of around 1 million base pairs, for example, 1 million nucleotides, for example, then we would need thousands of gigabytes just to hold that matrix in memory. And typically we don't have thousands of gigabytes available on the RAM memory for the computer, and even if we use hard drives for this, then things will take a lot longer, and this requires lots of resources for computing in this way. So this is where Hirschberg's algorithm is useful to avoid requiring so much memory at the same time. We still need to do all these computations, so we need to take time to compute the alignment, but we don't need that much memory used up at once in order to be able to follow the algorithm. So the basic idea here is, suppose we just want the alignment score between these 2 sequences. In that case, we do not need a complete matrix. So we can start by filling in this top row, and then we just start with this value, and we can fill in the second row by computing from the 3 possible previous alignments, use the maximum, either with the gap penalties or the matches and so on, the same functions that we saw before. In this case, we're doing the complete alignment, so not the local alignment, but the full alignment with the complete sequences. But we can compute this second row just based on the first row. In fact, for each value here, we could even discard all previous values, because to compute this one, we only need these values here. And then we can just compute this -1 using this one, replacing that -2 with this one and discarding the -2. So while we loop through this line here, we can keep discarding the previous values. But then when we want to compute the next row, we can just reuse the memory we were using for the top row here and copy these values there. So we discard what we had before, and now we compute this row here. And we keep doing this, and you see that at any given time, we only need to store at most 2 rows of the matrix. We don't need the whole matrix there. In fact, we can even optimize this and just store 1 row of the matrix and 1 value as we go through computing this row. So this would be, if we needed just the score, we could cut down on the amount of memory we would need to compute this. The problem is that when we reach the end, we do not have a way of doing that backtrace in order to find the alignment. So we know what the score is. The score of alignment in these two sequences, the global alignment score is 3 here at the corner, but we cannot tell how to align the sequences because we did not keep track of the whole matrix, so we don't have the information necessary to do the backtrace. But still, we can compute this score in this way without all that memory requirement. So the advantage here is that if we put the smallest sequence there on top, we would just need basically the length of that sequence. In fact, here we are using twice the length, but we could optimize this and basically just need the length of that sequence to do these computations. So this, instead of taking m times n memory, takes on the order of the smallest number between m and n. And this is a lot less memory that we need for the alignment, so it allows us to align large sequences. But the problem now we have to solve is how can we get the actual alignment, since with this way we only have the score. So this is the idea of Hirschberg's algorithm. We start with two sequences, A and B, and now we're going to do this recursive algorithm like this. We're going to split A in half. We're going to put one half on one side, one half on the other, and we choose this value here, where this position I, where we're going to do the split. Now, if we split A on position I, there must be some position J for B, for which what comes before J is what aligns with what comes before I on sequence A in the optimal alignment, and what goes after J is what aligns after I in the optimal alignment. So there must be a J so that the alignment, the optimal alignment of using the Needleman-Wunsch algorithm between A and B would be just a concatenation of the optimal alignment of A from the beginning to I and B from the beginning to J, plus the rest, which is A from I plus 1 to the end, and B from J plus 1 to the end. So there must be a J that fills this requirement, because in the optimal alignment there is something that is matching I, and there is something on the B sequence that goes on from here to the end. Even if it may happen that B is at the end or at the beginning, but we can put it somewhere, we can put J somewhere on the B sequence. Also, if we find the correct J for this, then the score for the global alignment will be the sum of the scores for these two alignments, the alignment before and the alignment after this split here. Because if any of these sub-alignments could be better, then we would just replace that in the optimal alignment and we would have a new optimal alignment. So the optimal alignment would not be the one we thought, there would be a better one. So if this alignment is the best between the two sequences, then there is this breakpoint where we have these best alignments before and after, and the sum will give us the score of the best global alignment. Okay, so the idea is that we arbitrarily break A in half, and then we find the J that does this, that gives us the maximum sum of the scores when we align one side with one side of A and the other side with the other side of A. And then we can do this recursively. We can keep splitting, and when we reach some sequence of length 1, we just sort everything together in the order that we split, and we have the complete alignment. So this is the basic idea for Hirschberg's algorithm. Let's start with the first part, which is computing these scores. We need to compute the scores for the alignments without having to occupy all of that large matrix of n times m. So we're going to use that trick, and this is basically the algorithm for scoring. So we start with an array S with the scores that only has 2 rows, and it has a number of columns equal to this sequence here, sequence B plus 1. So it includes that gap there. And we're going to initialize the first row of this array to these values just with the gaps. So exactly the same way we were doing with the Needleman-Wunsch algorithm. Now we're going to loop through all the elements of sequence A, and we're going to start by putting in the first value on this row, on the second row of S, as equal to the value on top plus the gap penalty. So this is the same thing as we would do when we initialize the matrix in the Needleman-Wunsch algorithm. But now what we do is we're going to iterate through sequence B, and we're going to compute all of these. So we're going to use the diagonal. So we go to the upper row and j minus 1, so the position before, and we use the match between the two symbols here to score if we came from the diagonal. And then we do the vertical and the horizontal, always adding a gap penalty. So if we came from here or if we came from here, we would add -2, which is the gap penalty. And now the score here at position 1j will be the maximum of the 3 that we found before. So this would give us -4, this one -4. Since this C is equal to that C, we count 1. So this goes from 0 to 1, and this one would be the maximum. So we have the match there. And now we keep doing this all the way until we reach the end of sequence B. So now comes the trick. We copy this array here, the first row of S, into the second row of S. Sorry, I'm using the zero base index like in Python, which you should have already seen by this time. And then we copy this into the first row of S. So now we are ready to go to the second element of sequence A, where now on the row 0 of S, this first row of S, we have the copy of what was previously row 1, and now we compute the new row 1 here, and we keep doing this. When we reach here, we copy it again, and so on until we reach the end. So this way we are going through the whole matrix. At the end, we have a vector which gives us the score of aligning this sequence with gap, this sequence with gaps and C. This would give us a -7. This whole sequence with gap CA, this would be -4. So we have all the scores of the sub-alignments of this whole sequence with the prefixes, the first substrings of sequence B. So this goes all the way to the end. If we align sequence A with the whole sequence B, we can get a score of 3. If we align sequence A with sequence B only up to A, there we get a score of 1, and so forth. So this is what we return at the end, and we have the vector with the scores of all these partial alignments. And now we're going to do this recursively. So first we have the alignment string for A and the alignment string for B. These are not the actual sequences, but are the sequences with the necessary gap characters in order to create this alignment. So basically a string that looks like this one we have here, where we have some gaps there so that we can create the alignment. So this would be the aligned string for one and the aligned string for the other. So we start these two empty, and now we need to check the terminal cases. Remember that when you're doing a recursive function, you always need to check if the recursion ended. So what ends the recursion? If there is nothing left on sequence A, so there are no more characters on sequence A, then the string for the alignment of sequence A will only have gaps. There is nothing more to align, and it will have as many gaps as there are elements on sequence B. The string aligned for sequence B will be just sequence B, because there is no need to put gaps in this one in this case. The same thing if the opposite happens. So if B is empty, then we just keep A as it is, and we fill in as many gaps as necessary on the alignment string for B. Another possibility is that one of these, either A or B, has only one symbol. In that case, if we are aligning a string with one symbol with a string with n symbols, we can just use the Needleman-Wunsch algorithm we saw previously, because that will give us just a single row or a single column, and it will not take up much memory. So we just use that and we have the alignment. So this would be the three different cases, and in which case we don't need to continue the recursion. So we end the recursion here. If not, if both sequences have at least two symbols, then what we're going to do is to find the midpoint for sequence A. This would be the integer division of A by 2. So we just take the integer part, and this would be the cutting point for A. And now we need to find the corresponding midpoint on sequence B. And this one will be the one that maximizes the score of the sum of aligning the left part of A with B and the right part of A with B. Now there is a little trick here that we need to reverse the sequences. I'm going to skip that for a moment just to explain the rest of this algorithm, and then we're going to focus on this trick. But the idea is that by this point, we found the correct position for breaking sequence B, so that what is to the left in sequence A and B have one alignment that we can just concatenate with the part that is on the right of sequence A and B, and this gives us the optimal alignment. So what we do now is we call the same function, Hirschberg, for the left part of A, which is everything from the beginning to the midpoint, and the left part of B, which is everything from the beginning to the midpoint of B, and this will be the left part of the alignment for A and B. The right part will be given by the same function, but using the sequence A from the next position to the midpoint all the way to the end, so mid A plus 1 to the end, and the same thing for B, mid B plus 1 to the end. And now we just concatenate the alignment, and then we return them. So the alignment string for A will be the left and the right added together, and the alignment string for B will be the left and the right added together. Now this is the tricky part here, is how we find the highest scoring value when we are aligning part of A, the left part of A, to the beginning of B, and the right part of A to the end of B. So we need to add these two sub-alignments in order to find the position with the maximum value. But note one thing. If we have the complete sequence for A, then we would have this score, which tells us what is the score if we align A with just this gap. So A is all gaps, is aligned with all gaps. This gives us -10. Or if we align A with just this part of B, just the C, and this gives us a -7 at most. If we align A with CA, and so forth. So this is what this score means. If we use just the half part of sequence A, then in that case we get this. So we just use, for example, suppose that we have the midpoint here at the second position, then the first score here would just give us this array, this vector, which means if we try to align CA with nothing, we get -4, CA with C, we get -1, so we have a C match, but then the A is left with a gap. If we have CA with CA, we have a 2, and so on. So this tells us what is the score of aligning this subsequence to the beginning of sequence B and moving forward all the way until we cover the complete sequence B. If we just did the same thing for the right part, we would get this here. So we would break this CAAT into CA and AAT, which would be this part here. And then if we scored it with this one, we would have the same thing. This would be the score of aligning all three nucleotides here with gaps, or all three of them with the C, or with the CA, and so forth. But we cannot really compare these two, because what we need here is to align the first part of A and find the best part of B on the beginning of B for the first part of A, and then the best part at the end of B for the second part of A, for the right part of A. And this would not work, because here we are starting also from the beginning of B. So these, if we just match these positions, we would be overlapping these two sequences, because both of them are aligning from the beginning. So the trick here is to reverse both of these sequences. I'm going to reverse A and reverse B and compute the alignment with the sequences reversed. This is the alignment score with the sequences reversed. So this means that I'm aligning from the end of the original A sequence and the end of the original B sequence. So if I now take this score and reverse it also, I can get the score for the right side, but it's going to be reversed. So what this means is that at this point here, I am looking at the score of aligning the left side with CA and the right side with TAAT here, because we are coming from the other side on the reverse. And in addition to that, when we reverse, we have this gap here on the beginning. So actually, when we reverse back, this one would be aligned with the gap. So these are all shifted one cell, which means that on this position here, the left side is covering all the way to CA, but the right side is only covering up to this T, so TAAT, and not DA, because this scoring vector got shifted because of the gap there. So this trick is a bit difficult to imagine, so you probably need to review this step by step, but it works in this way. If we reverse the two sequences and then reverse the scoring vector again, we can just add these two scoring vectors and take the maximum value, the position of the maximum value. So this argmax is the position of the maximum, for example here or here, this would be equivalent. So these add up to 3 and these add up to 3 too. So either of these points would be a good place to split the B sequence and give us two sub-alignments. So the left part with of A with the left part of B, and the right part of A with the right part of B, so that they are still part of the optimal alignment of the complete sequence. Okay, so this is the trick for Hirschberg's algorithm, and what we do now is, since we found where to split B, we split A and B into these two parts. We call recursively the same function to give us the alignment for each of the two parts, and then we concatenate everything. So this will be going down the recursive tree until it finds one of the terminal cases, and then it goes back up, assembling all of these alignment strings until we have the alignment at the end. So to sum up the algorithm, we are recursively breaking A in half, finding the optimal point to split B, so that we guarantee that the part before B is the one that before J in B is the one that aligns with the part before I in A in the global optimal alignment, and the same thing for what goes after. And we keep splitting this until we reach sequences of length 0 or 1, and then in that case, if it's 0, we just fill the other with gaps, or if it's 1, we just use the Needleman-Wunsch algorithm at that stage. And then we keep joining together the segments of the alignments until we reach the final global alignment. Okay, so this still takes on the order of m times n computation. So the time complexity is still m times n, because we still have to do all of these computations for all the sub-alignments that we are finding. However, since at each stage we are only using one row, we can use two, but it's one row plus one variable if we want, plus one number. So since at each stage we are only using this, for the computation of the matrix, we will only need to use the size of the smallest sequence. If we put the smallest sequence on B, that is the size we need for all these computation vectors. Because every time we call these scores here, so score this, we do the score and then throw away those vectors, so we don't need to keep storing everything during those inside those matrices. So this will be on the order of just the smallest of the sequences for the memory, for the space in the computations. Of course, we also need to store the complete sequences. We store two vectors of scores and things like that, but this is just a constant factor, and it will not be a problem here. So basically, if we have two sequences of around 1 million symbols, then we need just a few megabytes to do the alignment, to compute the alignment, instead of thousands of gigabytes we would need if we were using the original Needleman-Wunsch algorithm. Okay, so before we move on to the substitution matrix, I'm just going to take here a side note about scoring gap penalties. So what we've been doing so far is we've been adding just a constant factor for each gap that we find. So basically we have that -2 penalty, and each gap character that we find, we add a -2. So the total penalty for the gaps in the alignment will be just that penalty multiplied by the total number of gaps in the alignment. This is not a very realistic model, because what gaps are telling us is that during the evolution of those sequences there were deletions or insertions in the sequence. And we can assume that occurring, a deletion or insertion occurring is a rare event, so it can have a large penalty, but it doesn't make much difference if it's a deletion of 5 residues or 6 residues or 10 residues. Maybe the simple fact that there was a deletion is more important than a small difference in the number of residues. So a more realistic function is to use an affine function, which basically works like a constant if there is some gap, and then another constant multiplied by the length of the contiguous gaps that we have. So if we have a part of the sequence where we have 3 gap symbols in consecutive positions, then we would use a small number multiplied by 3, for example, minus 0.5, but then add a large constant penalty, for example, minus 10, just because we have an insertion or deletion there. Now, this complicates the alignment algorithms a bit. Basically, you're going to need an additional matrix and extra bookkeeping for this. We are not going to go into detail on how to do this in practice, but I just wanted to warn you about this. We've been looking at a simplified case so that we can focus on what's important on the algorithm. There are these additional complications in practice, so if you use a more realistic gap model, the algorithm becomes a bit more complex, but the basic idea is the same, so we're not going to spend time looking at these details. Okay, so moving on to the substitution matrix. What we've been doing so far is just to use this rule. If the symbols are different, we put a penalty of -1. If they are identical, we add a bonus of 1. So this would be a matrix like this. A with A is 1, G with G is 1, C with C is 1, and so on. And A with G is -1, A with C is -1, etc. But this is not a realistic scoring matrix because there are differences here. For example, mutating A to G is exchanging a purine for another purine. So this is a transition here. Transversions exchange purines with pyrimidines, for example, A with C. So if you have here, for example, in a more realistic scoring function, if you have adenine and then substituted by guanine here, this is only a -1 penalty. But if you have adenine substituted by cytosine, this is a -3 penalty because now you're mutating from a purine to a pyrimidine, and so there is more stronger selection pressure to eliminate these kinds of mutations. So basically, this would be a more realistic matrix, where you have a high score here for preserving the same symbol, so the same nucleotide in this case, and then you have those penalties that depend on the kind of mutation that is occurring. Of course, you can also imagine this with proteins. In this case, we would have 20 different amino acid types, but the idea is the same. So how are these matrices computed? The general approach is to consider what is the probability of substitutions occurring. So we can compute a matrix of this kind where these numbers reflect the probabilities of an A remaining an A during evolution or being substituted by G and so forth. Of course, since we are scoring things by adding all of these penalties and bonuses, we are not going to use the probabilities themselves, but the logarithm of the probabilities, because adding the logarithms is the same as multiplying the original numbers. So if we were dealing with probabilities, we would be multiplying them. Dealing with logarithms, we can just keep summing everything up, and we have less problems with numerical issues like underflow or overflow, things like that. And we can just use these scoring matrices to keep adding the contributions of all of these substitutions. So this is the basic idea. To compute a substitution matrix, we are going to take the logarithm of the probability of exchanging some symbol I with some symbol J. This can be an amino acid residue in the case of proteins or nucleotides in the case of DNA, divided by the product of the probabilities of finding a residue of type I and finding a residue of type B. So this is calibrated according to how common or rare the residues are. For example, if you have something involving, say, mutations in tryptophan, which is a very rare amino acid, this will have a very large score because of this calibration. Because usually whenever tryptophan appears, this is a place that is probably very meaningful for the protein and tends to be conserved. On the other cases, if you have things like lysines and so on, which are very common, they will have a smaller impact on the scores. So this is the way to compute the score on each position. Take the probability of some change, divide by the product of the probabilities of the residue types involved, and take the logarithm, and this is how these matrices are computed. Of course, to estimate these probabilities, we need to measure the frequencies of these substitutions. So we're going to need to look at actual sequences, align them, and then measure the frequencies. We can immediately spot a problem here, which is, in order to align sequences, we need the substitution matrices, and in order to compute the substitution matrices, we need to align the sequences. So the first proposal here, this point accepted mutation or percent accepted mutation matrix, was computed using very similar sequences, and it was estimated with some probabilistic model of the mutations in order to calibrate them so that PAM1 corresponds to one mutation in the DNA for every 100 amino acid residues. So these were protein sequences. The idea of accepted mutation is that it is a mutation that was accepted by evolution, so it survived, and we can see it on the protein sequences. And if we take a set of protein sequences that are very similar to one another, it's very easy to align them because they only have some small point substitutions occasionally, and so we can start from there, from that alignment, to compute the substitution matrix. So this was the idea for the PAM matrix. PAM1 is calibrated to one mutation for every 100 amino acid residues. Remember that this is a mutation on the DNA, and each amino acid residue corresponds to a codon of 3 nucleotides. And as we accumulate mutations on the DNA, we start having mutations occurring in positions where previously other mutations have occurred. So, for example, if we have a PAM 250, this means that we have an average of 250 DNA mutations for every 100 amino acid residues, but this still corresponds to about 20% protein identity, because some of these mutations reverse previous mutations. They occur on the same DNA position. Some of them do not change the residue because they alter the codon to a codon that is synonymous, that has the same residue type, and so on. So this would be more or less a correspondence between identity and the PAM number. But the number here on the PAM matrices is a calibration to what is estimated to be this number of mutations for every of DNA mutations for every 100 amino acid residues. Another type of matrix that is often used, this blocks of amino acid substitution matrix, which were calculated from this database of protein sequences. And the different numbers that occur here in the blossom matrices are the values of percent identity that are used to group families of sequences so that each family only counts as one. So, for example, blossom 62 means that all sequences with more than 62% identity among themselves count only as a single sequence. So they are weighted down on the average, on the computation of the substitutions, so that they count in total only as one. And these were calculated from sets of alignments and computing. So if we have the alignment of a large number of sequences, we can count all of these substitutions that we find. So the relation between the two is a bit inverse, because as we decrease the number here on Blossom, we start grouping together more and more families or larger families of similar sequences, those count as one, and we start giving more relative weight to more divergent sequences. So if, for example, we just we bring together everything that is 45% or more identical, then we are left with families that are very different from one another, and we are not considering, not giving weight to comparisons between very similar sequences. So this is one reason why, this is a reason why when we reach these low numbers of BLOSUM, we are looking at highly divergent sequences. And this roughly corresponds, so BLOSUM 45 roughly corresponds to PAM 250 in the divergence of sequences it's considering in order to compute those mutations. As we increase the number of the BLOSUM matrix, we are starting to group smaller and smaller groups of families, of sequences into smaller families. And so now we are counting increasingly small differences between these families of sequences. So we start getting a matrix that is more biased towards similar sequences, and so it's more close to what we have in the PAM lower numbers. So this is just an approximate correspondence, and we're going to see just in a bit why this is important, but this is to give you an important idea that when we are doing these computations, computing the frequency of changes from one residue to the other, if we are using very different sequences, we get lots of changes, whereas if we are counting mostly similar sequences, then we have many cases where the residue is the same before and after. So this will affect the difference here between the diagonal and the rest of the scores. If we are looking at very different sequences, the diagonals will go down and the rest of the scores will move up in value because those things become more frequent. If we are looking at very, very similar sequences, then the diagonals will be very high because more often we find the same residue in both sequences in the same place. And then these scores will go down because these mutations become increasingly rarer. Okay, so these are the two initial ones, or classical approaches. PAM uses explicit probabilities models to estimate that relation between the mutations in the DNA and what we are looking at in the proteins. BLOSUM is more empirical. It's computed from sets of alignments, grouping together families of sequences by different levels of identity. And experimentally, it seems to work a bit better than PAM. But there are more modern variations. So these Gonnet matrices are similar to PAM, but use more data and have this iterative refinement. Because as you can see, in order to compute these matrices, we need to have the alignments so that we can count the mutations. But for the alignments, we need the matrices. So with Gonnet, they did this iteratively. So they used the matrix for computing the distances between the sequences and recalculate the alignments, and then use the alignments to recalculate the matrix, and did that until the values converged. So they got a fixed result. VTML is again similar to PAM, but uses a better model for trying to find the best alignments and the matrices and so forth. You have very many variations here, but the basic idea is the same: is to look at the alignments to try to find those frequencies, to measure those frequencies, and then convert that in those logarithms of ratios between the frequencies of the different mutations and the base frequencies of the occurrence of those residues. Okay, so why is this important? When you are doing an alignment, it's important to select an adequate substitution matrix. So basically we can think of this as shallower matrices that were optimized with very similar, were computed from similar sequences, so they are optimized for similar sequences, and they are called shallower because evolution was not as deep in that case, so divergence was not as great. These tend to have larger scores on the diagonal and greater penalties for replacements, because when we use a family of very similar sequences, the frequency of substitutions is small, and so they tend to give you shorter alignments. For example, if you're using local alignment, you find shorter regions if the sequences are not very homologous, but you have greater statistical significance on the alignments that you find, because you have all those high scores whenever you find similarities in the sequences. You can choose deeper matrices when you have more divergent sequence, more dissimilar sequences. These are deeper because evolution went deeper in these cases, so the sequences diverged more. And if you use more divergent sequences to compute the substitution matrices, you tend to have smaller penalties for substitutions, for replacements of different residues, because these occur more often in those groups of sequences, and you'll have a smaller bonus for keeping the same residue constant. So this tends to give you longer, well-aligned regions, even if the sequences are not very homologous. However, it gives you a smaller statistical significance for smaller alignments, because now things start appearing closer to random when you are looking at those scores. We're going to see a bit more about this statistical significance when we look at sequence search, but the idea is that if you have a score that is very close to what you can get at random, then it's not very significant that you have an alignment with that score. On the other hand, if you have a score that is much higher than what you can get at random, then this suggests that there is really something there in the similarity between those sequences. So basically, shallow matrices could be these, PAM20, VTML20, or something like that. These are good for aligning highly homologous sequences or finding highly homologous regions when you do local alignment. These are not very good when you have different sequences that are moderately different, so more divergent. Deep matrices like these, for example, Blossom 62 or 50, these are good when you're trying to align sequences with low identity or finding homologous regions in local alignment with low identity, but there is some danger that you start aligning things that really should not be well aligned, because now it starts to be too permissive and can overextend the regions of alignment. Okay, so to sum up this part, we saw in this lecture and the previous one how to align sequences using dynamic programming. We use the right ordering of solving these sub-problems and take advantage of this optimal substructure of the problem, so that when we fill that matrix, we don't have to repeat the same computations over and over again, and we get the result in a time that is proportional to the product of the length of the two sequences that we have. We also saw a variant today, local alignment. It only aligns the best matching segments of the sequences, but it's basically the same algorithm. We just have that additional 0 there when choosing the maximum. And we saw Hirschberg's algorithm that allows us to avoid the big problem of requiring lots of memory space to store the complete matrix. So in this case, the time complexity, the time it takes, is the same as the other alignment algorithms we saw, but the space requirements is proportional to the smallest of the two sequences. So it can save a lot of memory, and it becomes practical to align very large sequences. We also saw substitution matrices, an idea of how they are computed. We are going to see this a bit in more detail in practice when we start doing Python exercises. And also I'm talking a bit about the need to select the appropriate matrix when you're going to do sequence alignment. But note that this part is already going a bit beyond what we cover in this course, because our focus here is on the algorithms themselves, the data structures, the implementation, and not so much on how you can use them. So I just give these hints sometimes, but in order to use these algorithms properly, then you need to really understand what kind of parameters you're using, in what circumstances you are applying them, and so on. So I recommend that you read Chapter 2 of Introduction to Computational Biology up to section 2.8, or the complete chapter if you want. I'll include on the lecture notes links to the original papers on global and local alignment. You can also take a look at those if you want.